Thanks a lot. So I will talk today about Oblivious Transfer from zero knowledge proof, which is a joint work with Garazzi, Muguruza, and Ferenc Pilman. So our work lies in the field of multi-party computation. In multi-party computation, you have multiple parties that tries to compute a joint function without revealing the input of any single party. So the typical example is the problem of the millionaire, where you have multiple parties that tries to determine who is the richest without revealing the fortune of any single party. So as I tell before, we can do that using multi-party computation, but it turns out that we can realize multi-party computation using a much simpler primitive that is called Oblivious Transfer. So in Oblivious Transfer, you have two parties. Bob was two bit strings M0 and M1, and Alice that wants to learn one of these two bit strings denoted by MB. So Oblivious Transfer has been, So in terms of security, we typically expect Alice to learn no information about the other bit strings, while Bob should learn no information regarding the bit B that Alice wants to learn. So Oblivious Transfer has been widely studied in the past because it is complete for multi-party computation. In particular, classically, we know that it requires some advanced assumption, notably trapdoors that lives in cryptomania. But on the other side, we know how to do it with only two messages. Quantumly, on the other side, we know that such advanced assumptions are not necessary, and we can do that using only hash function, for instance. But historically, there are no known message-efficient protocol known. So the historical protocols needed 7 messages. And recent work by Agarwal, Bartusek, Khurana, and Kumar manages to go to 3 messages. Another great work presenting earlier this week manages to do bit strings Oblivious Transfer with 2 messages as well, but in the pre-shared EPRPM model. But so this former paper raises the question: is there an Oblivious Transfer protocol that can be done with only 2 messages without any structure? So in our work, we answer positively to this question. So we show that there exists a 2-message Oblivious Transfer protocol that is secure in the random oracle model, assuming the existence of a hiding collision-resistant hash function. So in terms of method, our approach manages to remove the cut and choose method that were used in all previous protocols by replacing it by a mix of classical zero knowledge and quantum protocol. And one of our core method is to prove a statement on the quantum state in a non-destructive manner. So more specifically, the task that we achieve is the following. So Alice will send to Bob a large quantum state together with a proof. And Bob will be able to do some checks on these quantum states. And after checking the proof, Bob will obtain a smaller set of qubits. And Bob will also be convinced that some properties are fulfilled on this quantum state. Notably, Bob can, for instance, check whether the first half of the qubit or the second half of the qubit are collapse, meaning that they are measured in the computational basis, or either Ket0 or Ket1. And importantly, this protocol is zero knowledge in the sense that Bob should learn no information regarding the set of qubits which are collapsed. So in practice, we can generalize further this assumption by proving any properties on the set of collapsed qubits for any set of predicates. And we therefore extend zero knowledge proof to quantum languages. So we define a complexity class in order to encompass this notion that we call zero knowledge states QMA. And so once we have this generic tool that seems quite unrelated so far with Oblivious Transfer, we build a compiler that takes any zero knowledge proof and turns it into an Oblivious Transfer protocol, but while mostly preserving the properties of this zero knowledge protocol. So in particular, if we start from a non-interactive zero knowledge protocol like the one by Unruh, then we get for free an Oblivious Transfer protocol that is optimal in terms of communication with only 2 messages. But if we take an Oblivious Transfer protocol that is secure in the plane model, then we also get a zero-knowledge protocol secure in the plane model. So more formally, this is like the exact theorem that we prove. We can see that most of the properties of the zero-knowledge protocol are preserved. We only add a single message of communication if we lie in the CRS model, or 2 messages if we want to stay in the plane model. And I put below a table where we give the different flavor of Oblivious Transfer protocol that we can get depending on the zero-knowledge protocol that we use inside. So I will now describe our method, but let me first introduce some notation first. So this, I will use this block sphere notation in order to represent a qubit with ket0 and ket1 represented in this vertical line, and ket plus and ket minus will be represented using this horizontal axis. And I will also abuse this notation in order to represent a superposition of arbitrary bit strings, with ket x and ket x prime being arbitrary long bit strings. I will represent a measurement in the computational basis using this pole, vertical pole, and an horizontal pole will be a measurement in the Hadamard basis with the outcome D. All right, so let me start by presenting a very naive Oblivious Transfer protocol that turns out to be broken. And then we will start to improve this protocol to make it secure. So let's say that Alice wants to learn, so let's say, for instance, that B is equal to 0. So she would like to learn the first bit strings. Then Alice will prepare 2 qubits. The first qubit will be in the Hadamard basis, and the second qubit will be in the computational basis. The exact value that is encoded in that basis doesn't really matter, so we will just call it R, and it should be a sample uniformly at random. Now, if Alice wants to learn the other bit string, so M1, then she will just flip these 2 qubits. Then, in theory, she should send some proof to make it secure, but let's forget about this proof of security for now. So Alice will just send these 2 qubits to Bob, and Bob will perform a simple operation. Bob will just rotate the first qubit depending on the value of M0, so he will apply Z to the M0. So you can see that because in this example, the qubit is in the computational basis, then after the rotation, the information on M0 is completely lost. On the other hand, Bob will also perform this same rotation, Z to the M1 to the second qubit. But this time, because the qubit is in the Hadamard basis, the value that is encoded in that basis will be flipped when M1 is equal to 1. So it allows Alice to recover the value of M1 by simply asking Bob to do a measurement in the Hadamard basis. So S0 will be equal to a uniformly random string, and S1 will have the nice property that it equals to M1 XOR R. And so Alice can recover this value by performing this simple computation. So there is a big catch to this protocol, which is that this protocol is not secure. So how can we see that? So it's simple. If Alice chooses to send a qubit that is in the Hadamard basis as well, so the 2 qubits are in the Hadamard basis, then the protocol is exactly the same. Bob has no way to check that 1 qubit was in the computational basis right now. And so the same protocol can be performed and allow Alice to recover the 2 values, M0 and M1, since the protocol is now perfectly symmetric. So now we see that there is a need to prove to Bob that 1 qubit is in the computational basis. Before going to zero-knowledge proof on quantum state, let me introduce shortly what is zero-knowledge in the classical setting. So in zero-knowledge proof, we expect, a verifier wants to check that some properties are fulfilled, like, for instance, that there exists a solution to a given problem. And we want it to be zero-knowledge in the sense that Bob should learn no information on the solution to this problem, like, for instance, the solution to this Sudoku grid. So I won't have time to explain zero-knowledge in details, but what is important for our task is to see that zero-knowledge protocols exist for any NP problem, even non-interactively if we use some construction like the Fiat-Shamir transform that was presented in the previous talk. So ideally, we would love to be able to do something similar, but on a quantum state this time. So how Alice can prove that one qubit is in the computational basis while the other is in the Hadamard basis. So in a previous work with Frédéric Grossens and Elam Kashefi, we showed that it was possible to prove such statements, but the problem that first this work required some lattice-based cryptography, so it means that we're back to trapdoors and structures, and this protocol is also not suitable for statistical security. But if you look carefully, we don't really mind that one qubit is in the Hadamard basis or not. What really matters is that one qubit should be in the computational basis. So it turns out that we can prove this weaker statement without using lattice-based cryptography. So let me describe our protocol quickly. So the idea now is to send a different state. So before, it needed, we were sending a superposition of ket0 and ket1. Now we'll append to all these elements a random bit string, W0, W1, and so on. And in this picture, I will put, when the bit string starts with 0, she will be depicted in green. And one of these bit strings must start with a 1, and we will say that it is a dummy 1 because it should be illegal to send that kind of state. So Alice will sample all these bit strings, and she will prepare these states, which is a superposition of ket0, W0 plus ket1, W1. And as before, if she wants to learn the other bit string, she will just sweep the position of these two states. And Alice will then send the hashes of all these bit strings. So she will hash ket0, W0, she will hash ket1, like the classical bit string, sorry, 0, W0, 1, W1, L, WL, and so on. And she will send these 4 hashes to Bob. And she will also send a proof. So this proof is a zero-knowledge proof, completely classical. And she will prove to Bob the following. So first, she will prove to Bob that she knows the preimages of all these hashes. And she will also prove to Bob that one of these hashes is dummy, is invalid, in the sense that it is its preimage started with a 1. So it is this hash here in red. But Bob has no idea on the position of this element. So then Alice will send this zero-knowledge proof together with the quantum state to Bob. Bob will just check whether the proof, the zero-knowledge proof is valid or not. And Bob will also perform a check on the quantum state in order to verify that this quantum state has some expected structure. So more precisely, Bob will check first that these elements are preimages of the list of hashes that Bob received. So he will hash ket L, WL in superposition and check whether it belongs to this set. So it will be the first step, and then Bob will also check that this W are not dummy hashes. So he will just check basically whether it starts with a 1 or with a 0. So Bob will do this check in superposition. So it means that he will come up with a new qubit here that will contain a 1 if the state was honestly prepared. And as a result, because like at least for honest states, you can always factor this 1 away because it will always be 1 in all the elements of the superposition. And therefore, after checking, like after doing the destructive measurement, Bob will not disturb at all the state that was sent before. So we are still here in a superposition of ket0 and 0W0 plus 1W1. You can also see that if Alice tried to cheat slightly, so if she sent, for instance, a superposition of these 2 elements, then after the measurement, if the test passes, then the qubit will be projected back to the valid subspace. So in particular, we will have no more elements that are invalid in this superposition. Okay, so right now at that step, Bob can be convinced that the quantum state that he received has some nice structures. But we would like, remember, to have just 2 qubits for bit string OT, for Oblivious Transfer, sorry. And so Bob will just measure this second register in the Hadamard basis in order to recover a 2-qubit state. So for that, he will just perform a Hadamard measurement, get the outcome. And you can see that this measurement might actually flip the encoded value. But this is not so much of an issue because Alice can actually recompute the correction that happens during that step. So at that step, we can see that this is already interesting. So we get at that step zero knowledge proof on a quantum state because Bob can be convinced that at least one of these two qubits is in the computational basis without knowing which qubit is in which position. And then we can follow as before, like the simple naive Oblivious Transfer protocol that we described in order to recover the bit MB. So this is the end of our protocol, great. So I summarize on this slide the whole protocol. So here, this part is basically when we sample the random bit string, then we do the zero knowledge proof on it, then we create the qubit, we send these qubits to Bob. Bob performs some measurements and does the Hadamard measurement and send them back to Alice after applying this rotation. Yeah. So let me just tell you a small sentence on the security proof. So we can prove the security if the hash function that we use is collision resistant hiding, and if the zero knowledge proof is a proof of knowledge. And we can even get statistical security if this assumption holds against statistically unbounded adversaries. So if Alice is honest, then why is it secure? Because intuitively, the zero knowledge proof is zero knowledge, so it doesn't add any information. Then the hash function is binding, so it means that the hash function are also useless for it's hiding, sorry, so it doesn't give any information to Bob. And then you can also see that these two quantum states are statistically indistinguishable, whether the first qubit is in the Hadamard basis or in the computational basis. So it means that B is unknown to Bob, and now you can also, great. And so now you can also see that if now Bob is honest, then Alice has no way to cheat. Why? So intuitively, if Alice tries to send another state, so a superposition of many elements, then after the check superposition. So it means that M1 is forbidden. All right, so I won't have time to go into more details, but we can actually generalize this notion to more general notion of zero knowledge on quantum state with on the quantum language, sorry. We can define similarly soundness, correctness, and zero knowledge. And yes, so I arrived to the end of my talk. So Oblivious Transfer with a structure in two messages is possible, together with zero knowledge proof on quantum state. So we have a bunch of open questions left, notably in order to characterize fully the quantum complexity class zero knowledge states QMA, and to study the role of entanglement that seems quite important for this protocol, and to study application, notably in terms of quantum money. So I arrive at the end of my talk. Thanks a lot for your attention.
Thank you, Leo. Do you have any questions?
Regarding Bob not being able to know which qubits or the values of those that Alice are sending, perhaps I'm missing something. But if she's sending 0 tensor plus versus plus tensor 0, it's possible for Bob to do unambiguous state discrimination on those. Sometimes it would fail, and he would disturb it, which presumably would give some failure or report probability to the protocol. But otherwise, he could exactly know which of those two inputs she sent, and then presumably learn everything. So am I missing something with this?
So we add random, so the basis is fixed, but the value that we encode in this basis is not fixed. So it means that in one case you have either ket0 or ket1, and in the other case you have either ket plus or ket minus. And if you compute the density matrix of this state, then it will be just the identity. So you have no way to know whether you receive ket0 or ket1 from ket plus or ket minus.
Okay. Thank you.
We have time for one more question. So you mentioned you'd like to reduce the communication complexity of some existing protocols. Are there any in mind that you'd be able to apply this to?
So first, like I would like to study because right now we are, so the zero-knowledge protocol that we use either requires some structure if we want to be in the plane model, or no structure, but then we need the quantum oracle model. So I would like to see what happens in the plane model. Like, I guess we just need to find some zero-knowledge protocol that doesn't need any structure and that exists outside of the plane model. So I guess it's like one part where we can already improve on existing protocol. And I don't know, I think that it's kind of related to quantum money, like if we can certify both the basis, is either in the computational basis or in the Adamor basis, then it feels somehow that we have enough structure to do quantum monies, but it might not be trivial to be able to certify both elements at the same time. So it's one thing that I like to study at some point.
Let's thank Leo again.